Alright, so let us look at this result that we had done earlier. What we had said was that if alpha 1 to alpha k are distinct eigenvalues and their geometric multiplicity is ni's, then you have summation ni number of such eigenvectors. So, we had so many eigenvectors with us, this is what we showed. So, therefore, from here as a corollary we can say that I forgot to say was that as a corollary if summation ni I is equal to 1 to k is n, which is equal to the size of the matrix, the size of the matrix, then A is diagonalizable, all right, because the idea was that A is diagonalizable if and only if it has n linearly independent eigenvectors, all right. So, diagonalizable if and only if A has n linearly independent eigenvectors, fine. So, the question is that when can this happen? What we know is that there is a notion of algebraic multiplicity. The algebraic multiplicity of alpha is they will add up to n because they are the roots of the characteristic polynomial and the degree of the characteristic polynomial is n, all right. So, from this I would like you to conclude that A is diagonalizable if and only if algebraic multiplicity of alpha I is same as geometric multiplicity of alpha I for all alpha I belonging to the spectrum of A, which we wrote it as sigma of A, all right. So, for every eigenvalue I need that algebraic multiplicity should be equal to geometric multiplicity. If there is even one eigenvalue for which algebraic multiplicity is not equal to the geometric multiplicity, I have a problem. So, all right. So, let me write that also. So, A is not diagonalizable if we can find even a single eigenvalue alpha of A or alpha belonging to sigma of A such that algebraic multiplicity of alpha is not equal to the geometric multiplicity. Is that okay? So, this is very important that you can go the other way around and say that since we do not have enough number of eigenvectors corresponding to the algebraic multiplicity, I do not have diagonalizability with me. Is that okay? So, that is very important. So, keep track of that and understand it, fine. Now, the next thing that we would like to look at what are called Schur upper triangularization. Schur upper triangularization. All right. So, recall we have done A equal to LU, A equal to BC, the rank decomposition, A equal to QR. We also saw that I can write A as S D S inverse for some diagonal matrix D, but then there was a problem in the sense that not all matrices can be made into a diagonal matrix, all right. I cannot have a basis for every matrix where it is a diagonal matrix, fine. There are a lot of stringent condition in the sense that I need to find n linearly independent eigenvectors. So, it is a bit tough and we cannot do it in a general setup always. So, what we go to what are called Schur upper triangularization. It says that every matrix, every square matrix can be made into an upper triangular matrix. So, made into means, so there is this word made into. So, what it says is that there exist a basis, ordered basis of Cn over C such that ordered basis C, ordered basis such that A with respect to BB is upper triangular, or in the language of matrix it is P star AP is upper triangular. So, in general it is not supposed to be P star, it is supposed to be P star in place of P star. So, it should be P inverse. So, it should be here S inverse AS in general, but for us, since I am looking at all right, so forget about this part I think. So, here P star is equal to P inverse, so that P is unitary. All right. So, what we are saying is that every matrix has this form, upper triangular form, and here B is an orthonormal basis. So, B is an orthonormal basis. Fine. So, let us try to prove it. Proof requires similar idea as we did earlier, but let us try to go it. We did the idea, similar idea in what is called looking at algebraic multiplicity is greater than or equal to geometric multiplicity. So, let us proceed coolly and carefully. I have a matrix A which is n cross n, fine. I do go to its characteristic polynomial P lambda, substitute to 0, get an eigenvalue, say alpha, fine. Once you have got an eigenvalue for alpha, obtain an eigenvector of unit length. So, I can get a vector, eigenvector. Now, I can divide it by the length of it to get it a unit vector. All right. So, now I have a vector u1 which is of unit length, fine. So, I have this set u1, a linearly independent set, and length of u1 is 1, fine. So, this will imply that this set, so this can be extended to form a basis of Cn over C, fine. Apply Gram-Schmidt's to this basis to get u1, u2, un as an orthonormal basis, fine. Is that okay? So, understand these things nicely. So, I had a characteristic, so I have the matrix A. From A I went to characteristic polynomial. From characteristic polynomial we got one eigenvalue alpha. For that alpha we got one eigenvector. Once I have that eigenvector, I can make it of length 1, and then I can extend it to form a basis of Cn, and then I can apply Gram-Schmidt's to get an orthonormal basis. All right. So, orthonormal basis is not important now, but we will see its use afterwards, fine. So, from here what we get is, I get a basis B which is u1, u2, un, I get a basis like this. Now, what is the matrix of A with respect to this basis? So, again we will write it twice so that there is a clarity again for you. So, A of BB I want to compute, which will be equal to A of u1, A of u2, A of un, and this has to be computed with respect to B, this with respect to B, this with respect to B. So, this is same as A u1 is, here look at this, alpha is an eigenvalue for u1. So, I get that is alpha u1 with respect to B. I do not know what is A u2 is. So, this with respect to B and so on this with respect to B. So, alpha u1 is nothing but alpha 1 0 0 0, fine. I do not know the rest, what the rest are. So, there will be something here and there will be a matrix C here that I get, fine. This is one way of understanding it. The other way will be to look at, as I said, I can from here write P as u1 u2 un, fine. Let us look at P star AP. So, this implies that P star P is identity, fine. So, this will imply that P star of u1 is E1 and P star of un is En. I will not be using so many of them, but at least you should know what they are. So, if I want to compute P star AP, it will be P star A of u1, A of u2, A of un. So, you can see that I am doing the same thing as BB here. I am not doing anything special, it is same thing doing here, fine, which is same as I can put P star inside. So, bluing. So, this is P star of A u1 is alpha u1. I do not know what it is. I do not know what it is, fine. So, this is same as alpha times P star of u1, again something here, we do not know what they are, but what I know here now is P star of u1 is E1, alright. Therefore, I get it as alpha 0 0 0 and I do not worry what they are. Is that okay? So, whatever way you want to understand it, but understand it, alright. Spend some time that they are the same thing in different languages. One is with respect to the ordered basis, the other is matrix multiplication, alright, fine. So, once I have got this, now I want to understand the eigenvalues of A and eigenvalues of B. Want to relate eigenvalues of A and eigenvalues of C. I want to relate the two, fine. So, what is the relationship? Fine. So, what we know eigenvalues of A, they are same as eigenvalues of this or same as eigenvalues of P star AP, because P star is same as P inverse, alright, because P was unitary, alright. So, therefore, I needed that part. So, unitary, P was unitary, fine. So, the eigenvalues are same. So, it means that eigenvalues of A are same as eigenvalues of this, eigenvalues of ABB is same as eigenvalues of this matrix, which is alpha here, star here, 0 here and C here, alright, fine. So, I can see here that since there is 0 here, so if I want to compute determinant of xi minus P star AP, it will be nothing but determinant of x minus alpha, something here, 0 here and xi n minus 1 minus C here. Is that okay? It will be determinant of this, and therefore, by expanding along the first column of this determinant, I get it is x minus alpha times determinant of this, alright. So, the eigenvalues of A are same as eigenvalues alpha. So, eigenvalues of A are same as alpha and eigenvalues of C. Is that okay? So, they are same and therefore, we can proceed further and then try to understand the next idea, fine. So, we have got hold of eigenvalues of A and we have got this also, alright. And our matrix is this matrix we need to understand now. So, what we do, we do not worry about this part, we only bothered about C. So, what we have done is from A, which was n cross n, now I need to look at a matrix which is n minus 1 cross n minus 1, fine. So, in some sense I can apply induction. So, I have gone from n to n minus 1, so we can apply induction. So, how do I apply induction? So, let us understand what is the induction, mathematical induction. Mathematical induction says that I have a sum statement that I want to make and it depends on natural number n, fine. So, here my definition is, or my statement is, my property is that every n cross n matrix can be written in terms of, or can be made into an upper triangular matrix. All that is my statement, that the given n, every n cross n matrix, all right, has a basis or can be written in terms of a basis such that it looks like a upper triangular matrix. So, a statement, let us write it, for each n and each matrix A which is n cross n, there exists a unitary matrix, unitary matrix U such that U star AU is upper triangular. So, that is my statement that I am making about positive integer n. So, I want you to look at the first step of induction, which is looking at n equal to 1. So, if I look at n equal to 1, then I know that everything is nice because it is a 1 cross 1 matrix, which is already an upper triangular matrix, all right. So, for 1 cross 1, we have already the result that it is a 1 cross 1 matrix, which is upper triangular, hence I do not have to do anything. The next step of the induction is that assume the result to be true for n minus 1 and lower size matrices, all right. So, assume, next step is to assume that it is true for the matrix of a smaller size, and we want it to prove it for n. So, now let us do that. So, from A I have gone to n minus 1. So, apply induction to get a unitary matrix U1 of size n minus 1 cross n minus 1 such that U1 star CU1 is upper triangular, all right. Upper triangular. Let me write this matrix as T1, fine. Is that okay? So, by induction I know the result is true for C, which is an n minus 1 cross n minus 1 matrix. So, for this matrix C, I can get a unitary matrix U1. What did I write? Just a minute. So, there is U1 here also, there is U1 here also, that will confuse. So, I need to write not U1, but say some P1. So, I have a P here, P1, P1, P1 here, all right. So, I have a matrix P1, which is a unitary matrix, so that P1 star CP1 is 0, all right. So, now from here I want to go to the matrix A, fine. So, define P2 is equal to 1, 0, 0, P1, fine. So, this will imply that, let us look at P2 star P2, this will be equal to 1, 0, 0 P1 star times 1, 0, 0 P1, which will be equal to 1, 0, 0 P1 star P1, which is nothing but 1, 0, 0 I n minus 1, which is I n, all right. Because we took that P1 was a unitary matrix of size n minus 1 cross n minus 1, therefore, P1 star P1 is I n minus 1, all right, fine. So, therefore, what we see is that P2 is a unitary matrix. So, starting with P1 I got P2, which is a unitary matrix. We also took initially this matrix as unitary, this P as unitary, fine. So, now let us multiply these two matrices, what do I get? So, I want to look at what is P times P2, is this a unitary matrix? So, let me write this as say some capital U. So, capital U star capital U is something but P2 of P star into P2 of P, which is nothing but P times P star P2 star P2 P, which is same as P star P, which is identity, all right, fine. So, therefore, if I take U as this, then I get everything nice. So, let us compute U star AU, fine. So, U star AU is nothing but U is P to P, so P will come outside, so it is fine. Look at it, P to P for me. So, P2 of P, or I should have written the other way around, I think. So, I should have written the other way around, P here and P2 here, because I wrote, I think, P1 here. What did I write there? I wrote P on the right, yeah. So, I should have written P2P here, so therefore, this should be changed, P2 here, P2 here. So, P2 star P and P2 will come here. So, P2 star P2 and this I will get, alright. So, I should have written here P times P2 star A P P2, which is same as P2 star P star AP P2, which is same as P2 star. Now, what is P star AP1? P star AP1 was 1 star here, 0 here, C here, and this is your P2. So, this implies U star AU. What is P2 star? Look at P2 star here. This is your P2. So, P2 star is 1 0 0 P1 star times 1 0 star C, and then P2 again. So, 1 0 0 P1, alright. So, let us multiply it out. So, this will be equal to this into this is 1, just look at nicely, this into this is 1, this into this is a star, I do not worry about it, this into this is 0, this into this is P1 star C, 1 0 0 P1, which is same as 1 here, some star, 0 here, P1 star C P1, which is nothing but 1 star 0. I wrote it as some T, I think, T1. I wrote it as T1, upper triangular T1. So, it is T1, all right, fine. So, what we see here is that this matrix is upper triangular as T1 is upper triangular, fine. So, let us look at nicely what we have done. This is a very important theorem. So, let me get into it nicely. First thing we did, we wanted to prove the Schur upper triangularization, that every matrix, so given a matrix A, there exists a unitary matrix such that P star AP is triangular. You can make it lower triangular also, but we have looked at upper triangular here, and P is unitary, P unitary, fine. So that I do not have to compute P inverse for me, otherwise everything is nice, no problem as such. Or what we are saying is that A of BB is upper triangular, or whatever you want to say, this is what we wanted. So, we looked at the eigenvalues of the matrix, we picked up the first eigenvalue that I could compute or I could find out, used it to get a matrix which was nice in the sense that I could differentiate alpha 1 here, or there was alpha 1 that I need to write here, alpha 1 here, and maybe somewhere else alpha 1, maybe alpha 1 here, and things like that, fine. So, I have this here with me. So, I got the first eigenvalue alpha 1, and using that orthonormality of u1 to un or the ordered basis, I could get a matrix of this size, all right. So, from n I could go to an n minus 1 by n minus 1 matrix C, apply induction to it and get my results, all right. So, the important thing was that I could get a matrix C which is n minus 1 cross n minus 1, I could get it, and the rest of the part, if I look at, everything was 0 on the first column other than alpha 1, fine. So, I was in the process of making it a upper triangular matrix, fine. Now, that was the first thing we observed. Second thing we observed was that eigenvalues of A are same as eigenvalues of C, fine. So, therefore, when I get the final answer, all right, the upper triangular matrix, the diagonal entries will be nothing but the eigenvalues of A itself, all right. So, that is important. The final matrix that I have, it will have on the diagonal only eigenvalues of A, it will not be anything different, fine. So, once I have understood that the eigenvalues are going to be the same, I apply the induction. So, I have applied the induction here. This induction I had also applied, if you remember, the similar idea was there when we looked at what is called LU decomposition. All right. There also we had done the same thing, that we went into a matrix which of the type this block matrix. We defined a block matrix 1 0 0 L, L for the lower triangular we had done, and then we had done all the work. All right. So similarly, so the idea of this, what is called a patching. So you do for something for a smaller matrix, and then you patch up with zeros and 1 so that you get some nice matrix. So we are patched up. So we have done what is called patching of P1 to get P2, which is the required property that we are looking at. Fine. So that was important for us, that we wanted it. Once we have done the proper patching so that P1 was unitary, so P2 is also unitary, I applied to it. All right. So from there we looked at this part, we defined U as PP2, so that P is unitary, P2 is unitary, so their product is unitary. We verified this also, and then you just applied the matrix, whatever it is, matrix multiplication. We just looked at the matrix multiplication and get our results. All right. You could have gone through the basis also and done some work, but that will require much more work, because I have to relate different bases. First add the basis B, then another basis, another basis. All right. So in place of that, I followed the idea of matrix multiplication here, so that the clarity is there. Just you multiply it, you can see that everything is coming nicely. All right. So what we have shown is that given any matrix A, which is n cross n, I have a unitary matrix. There exists a unitary matrix U such that U star AU is T1 an upper triangular matrix. All right. Very, very important. The diagonal entries of T1 are the eigenvalues of E. All right. Fine. So we will look at a lot of application of this in the next class. What is called, we will also prove what Kelly-Hamilton theorem using this idea. We will use this. We will also be able to say that all symmetric matrices are diagonalizable, all skew Hermitian matrices are diagonalizable, and all of them, they come from a set, what is called a set of normal matrices. So normal matrices are diagonalizable. We will prove it. We will define what is called a normal matrix and prove all those things. All right. So that's all for now. Thank you.